Good evening, everyone. Just a few lines to introduce myself. I'm Giuseppe Petricca, and I am a multi-role operator in Raspberry Shake Company. Originally I was born, I grew up in Italy, and then after, let's say, my first degree, I moved to the UK to complete my studies, then found a job, and now working for Raspberry Shake. What exactly does Raspberry Shake do? What's the idea behind it? The idea behind it, let's say, originated around 2014, 2015 from our CEO, Brandon Christensen. And he was looking for a way to enable a more dense network of earthquake data recording, detection, analysis, also earthquake early warning networks. And there was an issue, the main issue being the cost. Just telling you this, when you actually want to buy a seismograph, you have different options from different companies in different countries around the world. But more or less, you would pay around $20,000 to $30,000 for a single unit. This makes very easy to understand why some organizations, some countries literally cannot afford this kind of equipment. So he started researching, he started jotting down ideas, he started testing things, and he came out with a very interesting concept that is using Raspberry Pis as a base to start building his own seismometer. And this idea more or less grew up and became less than idea, more practical. And in 2016, our CEO, together with other two or three, the company was very small at the time, two or three enthusiasts, opened a Kickstarter profile page, asking people, do you want to support us? Are you interested in earthquakes? Do you want an earthquake detecting device that will enable you to detect earthquakes even from the other side of the world? Response was outstanding. And the entire thing was funded in literally no time. And now you will see this in just a bit in my presentation. Now there are more than 2,500 Raspberry Shakes all over the world. And for some countries, Raspberry Shakes actually outnumber their government-issued seismic networks, which is probably one of our proudest achievements. So, as I say, let's get into it. And a simple question to start with. Why measure earthquakes? Why it's important? Why it's essential in some cases? First thing is obvious. We want to understand how our planet works. We know many things, but there is still so much more that we still need to explore and analyze. Furthermore, measuring, studying, detecting earthquakes will help the overall global scientific progress. And we already have seen this in many peer-reviewed papers that have been published thanks to the help of Raspberry Shake devices. And you will also see this in a bit in the presentation. Then there is also risk assessment improvement. And this is actually quite essential in countries that didn't have a seismic network before, or if they had it, it was very sparse and not that much dense, like, for example, Nepal or Haiti. It's also educational. We have had many professors, teachers from all kinds of different schools, all kinds of grades, from elementary to college level, that are interested in promoting how studying earthquakes is essential in some areas of the world, especially with young students that are very interested in pursuing this kind of career. And there is also much more. And everything can be pointed out at this simple graph or plot or chart that probably you have seen on websites when there were earthquakes, or on television when there were reports of earthquakes. This is what we call a seismograph. There is a trace detected by sensors of a seismometer that is actually plotted on a piece of paper, or in, well, most recent years, digital way. So what's Raspberry Shake? And it's pretty straightforward. It's, as written, simple and powerful personal seismograph, all based on Raspberry Pi. It's available in two different configurations. That is, indoor, if you simply want to have it, like, for example, I have it just behind me in this room, indoor, working with no trouble. Or, as we will also see, many people are interested in having it outside, out in the field. And for example, we have had this model that you can see at the bottom of the two, deployed more or less anywhere, in caves, on volcanoes, in some experiments underwater. Pretty versatile. And everyone can use it because it's very simple to use. So hobbyists, schools, DIYers. I built my very first one. I built it myself, buying a DIY kit, even before I started working for Raspberry Shake. Obviously, scientists, scientific research. There's very much, quite the number of applications. And now let's dive a bit deeper in and see what's inside. And probably you can already recognize some elements that are that build up a Raspberry Shake itself. So we have a Raspberry Pi, which is the heart and the mind of the Shake itself. Above it, we have what we call a shake board. That is our patented electronic board that is also available in various configurations, depending on which model of the Raspberry Shake you're interested in. And to complete the overall pictures, we have sensors. And also, these kind of sensors are different models, different types for different applications. And let's see how it works. Well, it all starts with ground motion. So any kind of vibration. We have had people that are not interested in earthquakes at all. But for example, they were interested in train vibrations because their house was built close to a railway tracks, and they wanted to see if vibrations were affecting the state of the house, of a building. Or for example, something more, it's not as much publicized, but analyzing nuclear test explosions. And or also something as, let's say, simple as just simply checking the traffic on the road in front of your building. There is much more than earthquakes. So that's why we tend to use the definition of ground motion instead of seismic motion. All ground motion is detected by sensors, by an array of sensors going from a single one to 4. And the data that these sensors generate is then analyzed and digitalized by our shake board, and then via the Pi sent to our worldwide network. As said, now there are more than 2,500 Raspberry Shakes all over the world. And there are actually many more than that number, because there are lots of institutions that do not share the data they're collecting with our global network. They are simply interested in collecting data for their own private use, so they don't share it with us. And let's go and take a look at the sensors, what they are and what do they do. The first one we have is called the geophone. And the geophone, as you can see, is quite simple. It includes an inertial mass that's suspended inside a cylinder via springs. And then we have a coil around the mass itself with a magnet fixed on the bottom. What happens is that when the inertial mass moves due to the change of generated by ground movement, then it generates an electric signal in voltage, which can be measured in volts. And then this electric signal is transmitted to the shakeboard. And with that, all the magic happens to make those simple numbers become an actual seismic plot. We also have accelerometers, which nowadays are more or less everywhere. We have them in our tablets, we have them in our phones, we have them in our smartwatches, in our cars, and their principle works more or less in the same way. We have a central mass in a dark blue color, connected, secured with a spring, and then we have fixed plates in a very small environment. What happens is that when, due to ground motion, there is a change in acceleration, then it's detected by the accelerometer itself, and this signal again is transmitted to our shakeboard and then to our network. And the last sensor that we have is actually not a sensor that one would expect related to earthquakes, which is an infrasound sensor designed to capture all very small atmospheric changes. In this case, we have implemented an infrasound sensors to better monitor volcanic activity, because volcanoes not only generate ground motion, but also generate sometimes quite rapidly evolving pressure changes. For example, I'm sure everyone remembers the Hunga Tonga explosion that happened some years ago in the Southern Pacific. That explosion was not only detected via ground motion, but was also detected on the other side of the world to the volcano, which is here in Europe, by infrasound sensors that were able to capture very small, we can also call them minute, variation in atmospheric pressure. And then probably the question becomes, what can you do with it? So I got one. What can I detect? Well, it turns out you can detect quite a lot. And we have prepared this, let's say, comprehensive infographic, dividing it between seismic in green and infrasonic in blue. And as you can see, many sources actually provide both data to us. They provide both seismic data and both infrasonic data. Naturally, you would expect that, for example, tornadoes, you would be more interested in the infrasonic aspect, as it's something that's 99% atmospheric. While, for example, you could say, okay, then a volcanic eruption, that's mostly seismic. But then when you study all the data set and we have saved in our servers something about 40 to 50 terabytes of data from all the Raspberry Shakes that have been online since 2016. So there is quite a mountain or a mountain range of data that sits there, and it's freely available to anyone who wants to analyze it. And we have had, in many cases, I remember one case in Norway and another case in along the English Channel, when meteors burning through the atmospheres were detected via infrasound. I live close to an airport, so helicopters and airplanes, they appear constantly on my Raspberry Shake. So as you can see, it's not only earthquakes, it's actually much, much more than that. And here's what I was anticipating just a little while ago. This is a map that is available to everyone. I will show you as soon as my presentation is finished. There are thousands of Raspberry Shakes worldwide that cover most of the world. We have our northernmost Raspberry Shake in Svalbard, which is more or less 80 degrees latitude north, and our southernmost one, which is actually in Antarctica, near a base that is jointly managed between Uruguayan and Argentinian governments. There are obviously, as you can see, the denser areas are the United States of America, Central America between Mexico and Panama, and the entirety of Europe. But we also have quite a bit of good number in Southeast Asia, in the Philippines, Japan, and actually quite a large number compared to the amount of people living there in Australia and New Zealand. Then, since everything that can be done with Raspberry Shake can be also classified as citizen science, what Raspberry Shakers have done with their instruments across these years? And well, more or less everything. And actually some of their application, they've surprised us, because we didn't even think about something that we're doing. For example, this is a very basic application. It is the seismograph of an earthquake. This was recorded by my Raspberry Shake here in the north of Scotland, of a magnitude 7 earthquake in Kamchatka, that is Russia far east, towards the international dateline. This was a magnitude 7, so quite a large event that was actually captured by Raspberry Shakes all over the world. And this is the basics that we can have. That is, all the signal that is detected by those geophones is then digitalized and can be read and plotted like it was an old-style seismograph on a rotating cylinder. In this case, we have also a direct display of where the energy of the earthquake appears, since we are quite far away from it. And I'll expand about this in a minute. When you are far away, all earthquakes appear at very low frequencies. Here we are talking something about between 0 and 3 hertz. If my station was much closer, then we would see a completely different distribution. That is, you would see these brighter colors much higher, actually reaching up to 20 or 30 hertz. Then, what we can do with this data? We can simply plot the epicenter and my stations on a globe to see visually see the distance between the 2 points. We can also plot how the waves of the earthquake crossed our planet. Because, yes, some of the waves actually walk, let's say, across the surface, but 90% of all the waves generated by earthquakes actually cross our planet. In this case, the first wave, the higher amplitude wave that we can see here, is represented by this blue line here that crossed the mantle of the Earth, reaching about 1,500 kilometers of depth before going up again and reaching my station. As you can see, this angle can increase depending on where the earthquake is with respect to your station. And for example, here in North Scotland, if the earthquake is large enough, meaning magnitude 6 or above, I can detect earthquakes that come from Fiji, which are more or less 17,000 kilometers away from where I live. Now, I told you before, shakes and sensors, they appear in various types of configurations. In my case, I have 3 sensors. One that detects vertical motions, so up and down movement, and 2 others, which are these other 2 channels plotted here, which detect north-south movement horizontally and east-west movement, again, horizontally. In this way, it's possible to capture the entirety of the movement that an earthquake, that a ground motion that an earthquake generates, because it's not simply up and down, but it's also ahead, forward, back and forward, and from a side to another side. When you combine all those 2 together, you can easily understand why earthquakes are so damaging close to the epicenter, because we cannot simply plan for a single type of movement. You actually have to plan for movement in a 3-dimensional space. And expanding on this, you can see here in these plots with lots of different colored tracks that represent how actually the earthquake made the ground here about 8,000 kilometers away move in a 3-dimensional way. Because otherwise, 2 of these plots would have been simply flat. Instead, as you can see, everyone moves up and down, right and left, north or south in a volume. And this is from just a simple sensor suite containing a Raspberry Shake that I have here on a wooden floor, not even in a professional seismic vault or anything else. And this is what makes Raspberry Shake powerful. It can be installed more or less anywhere, and it will give you very useful data. Just to give you another example, we have one of our most enthusiast Raspberry Shakers. He lives in Tokyo, and he has his shake on a shelf at the 26th floor of a skyscraper. And obviously, you will say, yes, he lives in Tokyo, so it's relatively close to earthquakes. Exactly. But that's also the point, because it means that with his shake, he can participate in any earthquake early warning system, because it's very close to the source of a possible event. And this gives you just an idea on how broad the span of applications that Raspberry Shake has. And then we also have the educational part. So we have Andrew Sheffer, which is a super enthusiast, and he lives in Western Canada, British Columbia, near to Vancouver. And he has taken on himself to give each school in the province a Raspberry Shake. And by doing that, it took about probably 4 to 5 years to achieve the initial vision of his project. And now is able to detect 75% more events than the government issued network in the same area. Also providing students from elementary school level to college level with an instrument they can initially just play with, and then they can use in their thesis. And for example, this poster that was presented at a conference, a seismological conference last year, was actually the result of a PhD study that one of his students completed. But many other things can also be done. For example, we had researchers from a university on the East Coast of the United States that left the Raspberry Shake for a year in a thermally isolated box in Antarctica. And then she went. After a year retrieving it, the shake was in perfect condition, and it gave incredible insight in what are called ice quakes. That is, all the ground motions and vibrations that are generated when ice fractures or cracks. Also, we had 3 collaborations with Berkeley University in Los Angeles, Southern California, about integrating Raspberry Shakes with their earthquake early warning networks. We also have studies in Samoa and American Samoa in the Western Pacific about earthquake monitoring and volcano monitoring in what they have called super remote locations. Raspberry Shakes were installed there with solar panels and batteries with a Starlink internet connection, and they were able to monitor volcanic activity that they hadn't managed to do it before, just because of the costs that normal and professional instruments and sensors would bring to their institution. And also, something that probably is not really a thought or something that people think about, but during the pandemic, people and researchers were able to see that the entire world was less noisy. Just because everyone was inside their home, and it was a measurable quantity that was easily visible across the entire planet. And studies like these, this is just one of many, where it will only be possible thanks to Raspberry Shake. And this is about research, but can we do also something fun? Something different, I don't know, amusing, or just as a simple hobby? Yes, we can. For example, we had people creating their self-made 3D enclosures for Raspberry Shakes. We had people building vaults, professional seismic vaults out of nothing. Simply taking an idea and say, okay, if I just dig a bit here and then build walls with concrete and then I put a pole in the middle, let's see what happens. We had many people doing that. Also, simple curiosity, just analyzing whatever signal comes out of a Raspberry Shake and trying to understand its origin. And also the application in terms of STEM into classrooms. So making children and pupils understand the dynamics, all the dynamics of the planet Earth. So this concludes my brief presentation. I'm leaving some links that are related to Raspberry Shake, our main website, our forum, our Discord server, and then Station View, Data View, which are our main data display front ends, and then our technical manual, if anyone would just take a look. And now, if you have any questions, I'm completely open, and I hope I can satisfactorily answer them.
Yeah, I've got a few questions. So how do you actually, what is the interface to the geophones? Like, is it just measuring voltage or what, how does that actually work? And what
So
is
all the
setting?
output that comes out of any sensor, so geophones, accelerometers, or infrasound, it comes out in volts. Then it goes through it goes, as I said, into our shake board, and in this process, then the voltage number, it's converted into an unitless again value that is called counts. Why do we do this? Because counts are actually the worldwide standard for any kind of seismic data. So when you have counts and when you know the specific of the sensors, which we do, then you can then convert the counts in whatever measuring unit you are interested in. For example, usually geophone data is converted into velocity, so meters per second. Accelerometer data, as the name itself implies, are converted into acceleration. And infrasound data instead is converted into pascals. Then also those values can also be integrated or scaled down, scaled up if you want to just calculate and obtain the ground displacement in centimeters and micrometers. You can do that. If then you want to combine different sensors, for example, if you want to analyze both the velocity and the acceleration that an earthquake generated in your area, you can do so by using, in the end, simple mathematics. So to reiterate, the process is ground motion is converted into voltage, voltage is converted into counts, and then counts is converted in whatever meters per second squared, simple meters, whatever measuring unit you are interested in for your study, research, or analysis.
Right. So the accelerometers, like how does the accelerometers fit into that? So why isn't the geophone enough by itself? Do you cross compare it or something like that? Or how does that?
That's a very good question. It's actually due to the fact that geophones are dedicated to small ground movements, while accelerometers are dedicated to large ground movements. And I'll explain this with a basic example. In 2010, there was a very strong earthquake in Haiti that unfortunately generated lots of casualties, but it gave us the example of a geophone, what we called saturating. That is, geophone can detect movement from zero, let's say, up to until a certain threshold. The threshold is not a constant because it depends on where the shake is actually installed, how the bedrock, how the foundations behind the shakes are actually structured. But beyond that limit, the shake the geophone will just display a flat output because the movement is so strong, so intense that it cannot keep track on it. When that happens, then the accelerometers get into play. And in fact, when you see accelerometers not recording any event, it just seems lots of noise, a thick signal with nothing in it, because accelerometers are not good for small ground motions. And so that's why we had to create one model which has all geophones dedicated to small movements, and then another model which has one geophone and three accelerometers to be able to capture both small and large ground movements.
Right. And then infrasound was it called?
Yes,
And also
infrasound.
it's other things.
Yes, infrasound. You can also find it on the internet or on some text called a microbarograph, because in the end, that's what it does. It simply detects very small variations in atmospheric pressure, which is caused, for example, by, as I said, a volcanic explosion. Also, for example, by windstorms. As I live here in the on the Atlantic coast, you all know that we have lots of windstorms in the northwest of the UK, and you can actually see them even before the windstorm arrives, because the wind that is pushing forward other air masses, or initially it's doing it in such small increments that you cannot see it with a normal anemometer, but you can easily track it with a microbarograph, that is, with an infrasound sensor. Again, the main occupation is to study volcanic eruptions from both close range, so let's say at the feet of a volcano, to far away range, that is, if the eruption is powerful enough on the other side of the world.
Right. So you somehow synthesize those three inputs, three different
Yes.
inputs
Yes.
come with one seismograph.
Yes.
And sorry, you showed one of the diagrams that showed you figuring out the path of the
Yes, I can go
ocean.
back to that one.
How do you know the path? Like, how does it calculate that?
The path, yes. So earthquake study is not an exact science. Why is this? Why is this? It's simply because we do not know as of now what actually, well, we do know what generates an earthquake. So the origins, we do know how that works, but we cannot predict an earthquake. We cannot say, hey, an earthquake will happen on that day with that magnitude at that time in that specific location. And so we have created, I'm talking about humanity, not Raspberry Shake, we have created models that simulate how an earthquake propagates through the earth as much as we can, and with as much fidelity as we can. And so, for example, we know that long earthquakes will have this kind of behavior because the path that crosses through the earth is actually the path of, calling between parentheses, less resistance for a seismic wave to advance compared to moving on the surface of the planet. Again, we have both. We have waves that moves on the surface and waves that go deep inside. You can see that, for example, here, not visible in the plot, but we have waves in green that go all the way down to the inner core of the Earth and then bounce back up to reach, in this case, my station, or in more generally, any location all over the world. And by studying how the waves that seismographs detect and record, we have actually been able, for example, to find this distinction between the outer core that is actually fluid and the inner core that is actually solid. And this happens because there are certain waves that are refracted by solids, but they are completely nullified by liquids. And so at certain angles, some waves will simply disappear because it will hit the fluids and be instantaneously dissipated. Other waves instead are not affected or are differently affected by a fluid compared by a solid, and then it will behave in certain other ways. And by studying the earthquakes for more than a century, we now have an understanding of how the inner structure of our planet is actually is. And so expecting certain kind of waves compared to other kind of waves, right now it's more or less a standard instead of an exception to the rule. So this is actually why we can, I don't want to use the word predict because we are not doing that, but we can know that certain waves behave in certain ways because of the type of, let's say, rock or solid versus fluid inside the planet that they are crossing.
So is that based on frequency then? So different frequencies travel different paths? Is that how it works, or is it?
That is correct. For example, as I said, if my station was closer to the earthquake, we would have seen. I can show you this because it's actually we can use some earthquakes that happened today. This was a 6.2 off the coast of south of New Zealand. And this is the closest Raspberry shake. And here you can see that the waves are much more pronounced because the station is closer, only 400 kilometers. But in the frequency range, the energy that this earthquake has pushed forward actually reaches value of 20 or more hertz. What happens, however, if we go farther away? So instead of 400 kilometers, let's go 1,400. So 1,000 kilometers more. And look at where the energy is right now. It's so flat to the very bottom of the spectrogram. If we were to go even farther away, for example, let's try this, now it becomes almost invisible. You have to really look at this. And if we try to move even farther away, we can see something, but actually it seems more or less the basic noise that this particular station has. So the farther away one goes, then the different, the energy just becomes distributed in a different way. And this gives us insight in how the waves are traveling through the planet. For another example, let's say after this was 1316 UTC, and then we had a 6.8 about an hour and a half after that, much more south. And for example, since this was much stronger, just to give you, every 0.1 increase is a 30-time increase in strength. So even if the difference is not quite a lot, it becomes rapidly big as earthquakes are concerned. And you can see we are 2,000 kilometers away, and the energy is still up to 10 hertz. While instead, this other one at 2,000 kilometers away, at the energy already to the bottom. If we go here, 5,000 kilometers away, we have the same frequency range that this other earthquake displayed at only 2,000 kilometers away. So this is just a very brief example of two earthquakes alone. So imagine that you're studying millions of them, and you are rapidly able to determine what's going on and start to approximate the earthquake wave propagation behavior with a mathematical model. And once you have that model, at least a start, you can then refine it until it more or less displays the same behavior that we can observe in nature. And the fact that we now have so many Raspberry shakes around the world, especially in areas. For example, we have a cluster here in Kazakhstan. They are not on the map because the institution is doing a private research, but we have about 30 shakes in Mongolia, which doesn't have any kind of government-related or created seismic network. We have had an incredible uptick in shake installations in Haiti after the 2010 earthquake because there was no seismic network there. They had one single instrument that was provided by the American USGS, but with a single seismometer you cannot do any kind of earthquake analysis. And more recently, you can see this is Jamaica, and you can already see 16 Raspberry shakes. 1 year ago, there was none. And again, Jamaica is a country that doesn't have a proper, let's call it, seismic network. Same thing could be said for Guatemala, could be said for Honduras, El Salvador, and many other countries, or maybe isolated installations. Like, for example, these two actually in American Samoa, in the middle of Southwest Pacific. So this is actually
So what's a little like one? Some say 4D, some say 1D.
Yes, those are all the types, models that Raspberry Shake provides. And 1D, it has a single geophone, so it can detect up and down motion small. This is our entry-level seismometer. Then we have a 3D, which includes 3 geophones, one up and down, one north and south, and one east and west. Then we have the 4D that has 1 geophone up and down, and then 3 accelerometers up and down, north and south, and east west. And then we have the B, which is an older model. This is the Boom. It contained a single infrasound sensor and nothing else, but this has been now discontinued because we don't produce it anymore. And we now produce, because there's more interested into that, the SMB, the Shake and Boom, which includes a single geophone, vertical, and an infrasound sensor. Because having both in the same instrument was more useful than having 2 instruments doing, in the end, the same job. And then you can also see some that are marked as a J. Those also were a previous model that is not in production anymore. Those were called the Raspberry Jam, with Jam referring to jam sessions. That is, you could connect any kind of sensor to this board and then calibrate it yourself. So you had to be a bit, let's say, proficient in electronics and also seismology. And then you could reuse whatever sensors you wanted or you had on hand without needing to buy anything else to just create your own personal seismograph. As you can see, those appear in color. The color displays the ground motion, and this is live. Everything that you can see here is live data that Raspberry Shakes are detecting. For example, I don't know, click this one in the southwest of England, and we can see this is live data, the last 10 minutes, that appear constantly streaming from any Raspberry Shake all over the world. And that probably, this range of instruments gives you an idea why we have so many terabytes of data available, because we are talking about almost 2,700 Raspberry Shakes, and in which most of them are 3Ds, so their data is multiplied by 3 compared to our standard 1D version. And we are talking about live streaming 6,200 channels of data at the same time. And I can tell you this has been a bit of a nightmare on server side, because managing that amount of data, it can be challenging. We are lucky that we live in the technological era that we are in, because even 10 years ago, this would haven't been possible at the scale. And more and more are being installed each day. For example, we had our very first Raspberry Pi in Kenya just installed 2 days ago. And there is also, we have an interested party in Zimbabwe that is monitoring mining activities. So right in the middle of Africa. We have researchers in France that has completely wired up and monitoring the Mayotte island. So the applications are quite a lot. The study that can be done is also quite a lot. And again, sometimes we are just surprised by some applications that shakers have taught. And we are like, oh my, that's really interesting. Or something like even revisiting old events or past events. As you can see, this map also displays, I'm just disabling the stations right now, it also displays a live stream of all earthquakes that are happening all over the world. And we, for example, this is only the last week, and there are 7,000 earthquakes on this map.
Wow.
And we are continually expanding the sources that this map acquires data from. And this is a task I'm personally involved in. Because this is already the most complete map of earthquake activity in the world. And we have calculated that we are still missing probably something around 50 to 70 data providing agencies that have still to be integrated into this kind of map. And naturally, if you have a Raspberry Pi, you can also contribute, because all the data you're putting forward helps refine earthquake detection. For example, we have this dense installation network here in Nepal that has helped detect something about 70% more earthquakes that Indian, Nepali, and Chinese government were able to in the same area. Just because there is a local network that is able to do its own local calculations. And that's probably why I feel having this kind of open network, open data access network, season size network is very important in this day and age, because it brings improvement, it brings concrete results. And for enthusiasts, for hobbyists, trust me, it also brings lots of fun.
Yes, there are some questions in the chat, so I'll just read them out quickly.
Sure.
So how is power supplied to the Raspberry Shakes located in remote locations?
That's a very interesting question. Let's say the most common way to do it is by using solar panels connected to batteries with voltage regulators. We have a couple of installations in the Italian Alps, also in the Swiss Alps, that are powered in that way. Then there was one person that I think implemented a mini wind turbine to provide power supply to their Raspberry Pi. In any case, for let's say small, quick installations out in the field, the quickest way that our shakers have done it is just by basically bringing lots of batteries and nothing else. Naturally, this is good for, let's say, very short applications. Otherwise, again, best way to do it is solar panels plus batteries and all the connected equipment.
Okay, there's a few more questions in there.
Sure.
Guess how accurate the alignment has to be, north, south, east, west. How accurate does it have to be?
Well, there are references on each Raspberry Shake so that it can be oriented properly. The orientation doesn't have to be like super perfect. It doesn't have to be to a tenth of a hundredth of a degree. The important thing is, for example, I have oriented mine with a simple analog compass to the north. And then it's also important to level the shake so it rests as level as possible. Because in that case, when it's not leveled or properly oriented, all the data it's recording is still good. But then you have to do some seriously heavy post-processing to better identify components, let's say north, south, east, west, vertical, because they weren't properly aligned in the first place. But I would say just a rough alignment to the north and a proper leveling, that's all you need.
Yeah. And also a question about detecting things like mining, quarries, fracking, and bombs, like in Ukraine, can you detect bombs?
Oh yes, that's entirely possible. For example, we have this network that you can see here in in Cornwall, in southwest of England. This network was, let's say, was created just to monitor quarry blasts in that location. Again, I mentioned the network in Zimbabwe that is monitoring mining activities. And we also have the network in South Korea that was born, let's say, more out of necessity to monitor possible nuclear testings of North Korea. We also have a network in Ukraine that has grown in the last, let's say, 4 to 7 months, more or less. And that it's also used to detect activity like, again, war-related, so like explosions, bombs, or other kind of, again, literally anything that makes the ground move.
Right. So there's a question about the smallest movement that can be detected. I guess that depends on how close it is. Is that like how?
Yes. For example, since we are here, here we are in the south of Poland, and we can see that we have very small events, magnitude 2 point something, 3 point something. Those would be detected by these close earth shakes. But or for example, we can go to Iceland, where we have 0 point something earthquakes, which are completely, you will not feel anything as a person, and even the most sophisticated instrument would sense them unless they were very, very close to it. So yes, if the ground movement is really small, it depends on how far away the epicenter of the earthquake is related to you, and also it depends how much noisy your location is. Because, for example, if you are in the middle of nothing, naturally your noise floor will be very low, and you will be able to detect fainter events. On the other side, and you're in the middle of the city, probably you would not be able to detect anything unless it was, I don't know, magnitude 3.5 or 4 and above that.
Yeah, so there's a question about that. I don't know if Anthony, you want to.
Oh yeah, it's
Yeah, Anthony's just asking about how noisy the signal is and how do you filter out stuff you don't want to see.
oh yes. This is also possible by let me go back to that to those big earthquakes in New Zealand. And we have, as shown, we have another instrument that's called the data view. And this allows you access to all the data from all the channels, from all the shakes, since the very exact moment the shake was first online. This is open, it's completely open. Anyone can go, anyone can see, and anyone can work on it. For example, these are those big earthquakes. Naturally, if they are close, okay, as you can easily imagine, you don't need any filter because the vibrations generated by the earthquake are way above your noise floor. But let's say that, for example, let's go, for example, no, let's go here. And this is another earthquake, but was farther away. And it still can be seen above the noise floor quite strongly, I'd say. But let's say now we wanted to analyze how this goes on a different frequency range. And for example, we want to analyze how it appears between 0.7 and 2 hertz, which is what we call a regional range. And regional is intended between 700 and 5,000 kilometers distance from the epicenter. And we can see that we still see very well the initial wave easily, but something else is popping out. Because again, certain waves produced by the earthquake appear or disappear at different frequency ranges. And if we take the same event from a different station, for example, let's say this one in Northern Australia, and we do the very same thing, we can easily see that, yes, that event is still here. You can see it in raw form. You can see the arrival of the primary wave here and the secondary wave here. But let's say you want to analyze what are called surface waves, which are very, very low frequency. We're talking about below 0.1 hertz. Then you can easily do so via data view, and look how much stronger the waveform appears for the two events. And if we do a simple comparison, actually, well, you could barely see them in the unfiltered data, but then when you filter it, they just pop out.
Right. It's very interesting. Sorry, we're gonna have to stop there.
I know. I think we can stay here for hours and talk about this. But in any case, if anyone has any question, we have our Discord. Let me put it up again so that people can have those links. We have our Discord. We have our forum. If you write in the forum or in the Discord, it will be probably me that replies. So feel free to ask any kind of questions, any curiosity, whatever you want. And we always do our best to satisfy anything that we receive. So
okay, there are a few questions in the chat that I sort of paraphrase, but there's a little bit more detail in some of them. So maybe for the next, when Romy does his talk, you can just go through the chat and add any color to those answers.
Yes.
Thanks very much. That was very interesting. I learned a lot.
It was my pleasure. I hope it wasn't boring for everyone. And
it was really good.
I'm sorry that we have a bit I've intruded on the time for our next talk. But yes, I will take care of replying into the chat questions while that. Thank you again. Thank you everyone, and thank you for having me tonight.
Thanks very much.